So I'm Alex. I've been working with Robin for my PhD on gamma ray binaries, and because of all the active OB stars in gamma ray binaries, we thought it would be a good idea to talk about some of them. So my overview of kind of this talk is I'm going to just very briefly go over our active B stars and the connection to gamma ray binaries, which is just they happen to be in them. And then I will talk about five different gamma ray binaries at kind of differing levels of detail. But I think all five of these have kind of interesting recent within the past couple of years discoveries that should be kind of at least talked about. And then I'll talk a little bit more about what current research is looking at for these. So typically looking at these emission features of strong H alpha and H beta lines due to this equatorial disk that has formed for these massive hot stars, O, B, and A type stars. Creating this equatorial disk that will then kind of interact with its environment, or if it's in a binary, it will then interact with the binary itself. And it's instead of an accretion disk, it is a decretion disk as this sort of ejecta from these stars exceed the breakup velocity and end up being governed by viscosity rather than gravity falling back inwards. And so when you end up having that kind of object in a binary, we're going to get some sort of interaction between this disk and the stellar wind and this compact object that might be in there. So we've already talked about BE stars in terms of X-ray binaries. Thank you, Jill, for that. And again, here's kind of the orbital period with respect to spin period, and we can see the different kind of correlations that exist with the BE X-ray binaries and the supergiant X-ray binaries. And they're typically always fed. All this high energy emission is generated by this interaction with the disk or the wind from this massive star. And so all these X-ray binaries have substantial stellar winds, but they really get kicked into overdrive when we start talking about high mass gamma ray binaries, which are typically these binaries with, again, an O or a B type star, eccentric orbits, roughly an orbital period of 1 to 100 days, although there are some exceptions. Pulsar J0632 is roughly an orbital period of 50 years. Something interesting is you'll get some really interesting modulation on X-ray, gamma ray, and radio wavelengths. And sometimes they'll be correlated, anti-correlated, depending on geometry. The SED of these kind of objects peak well above 1 mega electron volt. So most of the energy ends up being way in the gamma ray regime. Now, the kind of classification of these types of binaries really depends on, well, one is their companion object, an O-type, B-type, sometimes a Wolf-Rayet can be considered, but also the particle acceleration method and the emission mechanism. And so there's been a lot of debate between two general types of models. And here's our nice little GIF of pulsar B1259 as it kind of interacts with this decretion disk. A lot of these sources also have associated radio kind of filaments or jets and TeV emission. So it's very, very fascinating to try to decipher the mystery of what is causing kind of all this emission. So here we have just a general SED showing the component from the massive companion in green, and then the synchrotron and inverse Compton kind of components that make up the rest of the broadband emission, going all the way down to radio, going to X-rays, MEV, GeV, TeV emission. As Joel kind of was talking about with standard X-ray binaries, there are hundreds of those. Well, there are only there's only about 10 gamma ray binaries. The classifications are a little bit tricky. Sometimes new binaries will be discovered and they have to go through this kind of candidacy period. But here's kind of what we are looking at. So this is in the middle of my screen. And I'll be talking about 5 of them. But before I dive into specific cases, I wanted to talk about the kind of what is creating this high energy emission. And it tends to be in one of 2 models, either a binary shock from a pulsar wind nebula that is orbiting this binary and that interacts with this decretion disk or just even stellar wind. Essentially, these relativistic particles get upscattered to high energies due to either some sort of equatorial current sheet or magnetic reconnection within the PWN, and then it starts interacting, creates a kind of a shock with this stellar wind or decretion disk. And kind of where this shock exists within the binary depends on the ratio of momentum fluxes from the companion star and the PWN. And this kind of shock will accelerate, will end up scattering photons up to GeV and TeV energies. The other option is the microquasar model, which instead of a neutron star kind of opts for a black hole compact object. And it is pretty geometry specific. Only specific geometries will really allow for this phenomenon to be observed. The radio jet powers most of the broadband emission, some of the X-ray there too, and then the relativistic particles accelerated by these jets will end up interacting with either this companion star's stellar wind or just the surrounding environment, and then that will generate the GeV and TeV emission. Here's a very nice image of a microquasar SS433 from the HESS collaboration. And here we can actually see kind of the compact object in the center here. And we have our X-ray jets after a break of seeing no X-ray jets. And they line up with our HESS contours. And all the radio emission kind of is in blue. It's a very pretty picture. Other sources that I'm not really going to be talking about, but you should keep in mind that do produce this variable gamma ray emission are obviously some of these gamma ray pulsars, some novae systems, colliding wind binaries like Eta Carina. Yeah, but for the most part, I'll only be discussing those 2 methods of gamma ray emission. So to start, I wanted to jump into some kind of like historical well-known gamma ray binaries, LSI 61303, which has a BE companion. The orbital period between the 2 is roughly about 27 days. It was thought to have a high eccentricity of about 0.5. However, maybe newer kind of models seem to cast that into doubt. Optical polarization suggests that this kind of high energy ends up coming from the interaction between this decretion disk that we talked about with this pulsar wind. This kind of object was long kind of thought to be a microquasar due to some flaring, but recent kind of analysis is starting to think it's indeed a pulsar compact object where the scattering of the stellar wind companion stellar wind generates a high energy emission off of either the corona or the neutron star, PWN. And so here we kind of have a binary diagram, orbit diagram, and we see kind of the radio contours that are that were observed in 2009. There are kind of updated radio contours from Dewan et al. 2006. They used a lot more eccentric model. So I've actually kind of taken these radio contours and I've changed them on kind of a new binary ephemeris here. So this is kind of what it would look like if you kind of hand wave and assume that the radio kind of contours don't change much. But interesting to note is that about this binary phase of about 0.6 or so, there's a radio observation from FAST in China that detected a 269 millisecond spin period in a 3-hour observation. So this kind of blows the whole microquasar scenario out of the water. However, it is the only spin period or pulsation that has been detected from this binary system, despite follow-up observations or other observations from FAST and other kind of wavelength searches. And the thought process here is that at this orbital phase, the PWN shock is actually kind of pushing away the stellar wind so that we can kind of get a glimpse into the closer to the pulsar. It might allow for detection of the pulsations. Here's that detection. We get the fast observation, the pulse profile on the top, and we get the dynamic pulse profile. So phases on the bottom here, and then time on the y-axis. And that recreated pulse profile looks like this on the top. Moving on, I move on to another BE type star. This is HESS J0632+057, which is another BE star with an unknown compact object. Orbital period of almost a year. So this is quite a long orbital period. The geometries are relatively uncertain, but it's presumed to be a high eccentricity of about 0.6 to 0.8 and a very high inclination. Over here, we can actually see the H alpha, H beta, and kind of the characteristics that helped us define, helped Zamenhof and co-authors define, and the preceding co-authors kind of determined that this was a BE star. There are two very pronounced X-ray peaks that are separated by about half an orbit in phase. There's almost no GeV emission detected, so this was actually a serendipitous kind of detection of this source. And there's correlation between the X-ray and TeV light curves. Here's an idea of what this kind of geometry is thought to look like. The disk in blue and the compact object moving around. Here are those X-ray and gamma ray light curves, TeV light curves. X-ray on the bottom, and we have this very noticeable spike, and almost we change our X-ray brightness by almost a factor of 10. And then we have our GeV, our MAGIC and HESS and Veritas detection up here, and we see pretty good correlation between the X-ray and the TeV light curves. Due to the correlation between the two, it's likely that the pulsar is interacting with this decretion disk as it kind of goes through this, as it passes through it, and it actually ends up ejecting some of this accreting matter out into the orbit, and then some of the after X-ray and gamma ray kind of emission is from interactions with those kind of clumps. It's called kind of a little bit of a propeller regime. In this case, the pulsar magnetosphere is actually shorted out, so it can't actually accelerate high energy. The pulsar itself cannot accelerate particles to high energies to radiate them away. Lastly, there was finally some GeV detection of the binary itself, and so we get actually two kind of flux data points at around that primary peak that I mentioned before. Although this might, this might change. I think I'm not so sure I agree with these flux points here. I think there's actually a detection for the second peak as well. But who knows? We'll find out in the future. Moving on away from BE type stars, I'm going to now change to O type stars as the companion object. We move on to pulsar B1259, which is a kind of this GIF that I showed earlier, a 47 millisecond radio pulsar with the pulsed emission. And when it starts interacting with this decretion disk, all of a sudden, non-pulsed emission starts dominating. It is a 4-year binary orbit with a high eccentricity and this inclined disk. It was discovered as a pulsar first and then a binary later. And here's kind of that pulse profile of the 47 milliseconds. The X-rays flare as the pulsar wind starts interacting with the decretion disk, and that will happen a few days before the periastron. We can see that here, kind of in the X-rays. And then a second X-ray peak will follow shortly after the periastron, about 10, 15, 30 days or so. And following that is the gamma ray emission. And at that first crossing of the periastron, we see radio emission down in the bottom start to flare up. The H alpha broadens quite a bit. And again, we're kind of experiencing this this opportunity to look deep into the pulsar magnetosphere as this kind of clone of the cone of shocked wind kind of gets in between the companion stellar wind and disk and the actual neutron star. So that is the explanation for kind of all this prolonged X-ray and gamma ray activity well after the periastron, well after the pulsar has passed through the periastron. Recently, there was an attempt to measure the polarization angle and degree during this periastron passage with HMXB, and it indicates a low magnetization at this binary shock. So it suggests that it would be an efficient acceleration for a perpendicular shock. And this is the first kind of X-ray polarization glimpse for any high mass gamma ray binary, but now it's being followed up, and there was some evidence for phase variability in polarization angle and degree in this paper by Phil Carrot. And now I think there is a follow-up study on LSI 61303. Moving on to LS5039, this is kind of an archetypical high mass gamma ray binary. In order to model the broadband SED, it's extremely bright and relatively stable in its X-ray light curves. It has a O-type companion, and it has no disk. So a lot of this gamma ray emission is thought to be coming from kind of clumps in the stellar wind and all this variability. It has a relatively short orbital period of about 3.9 days, not 3.6 days. And so that's actually the shortest kind of gamma ray binary, an orbital period. Interestingly, a couple of years ago, there was a detection for a 9-second spin period with Suzaku and NuStar data, inferring the existence of a potential magnetar compact object. However, follow-up kind of analysis showed that maybe instead of a strong detection, that is more of a signal or a statistical excess. But it was a little uncertain. So these Suzaku and NuStar observations are kind of giving conflicting answers on what this kind of 9-second spin period is. So a second NuStar observation was done, really showing that the orbital or that this spin period is not so significant at all. Here's that actual second NuStar observation. It's taken 6 years after the first NuStar observation that did show it. And a lot of this is still uncertain. It doesn't seem to show any strong signal, but that could also be the result of a improper ephemeris that was used. Unfortunately, the ephemerides have not been updated for LS5039, and doing so with only kind of an X-ray or Fermi or gamma ray data would be quite computationally expensive. But for now, it is likely a statistical excess. It is, again, like I said, very highly sought after to do the SED modeling. It's been labeled as intrabinary shock, microquasar, and more empirical models, but typically all these models tend to underpredict the MEV and GeV emission. Hopefully, though, because it's been quite some time since it has been studied with all this Fermi data, there's just so much more data out there. There's a lot that can be expanded upon. Here's kind of the phase resolved Fermi-lat spectra evolution with about 16 or 17 years of data, and it's far more kind of comprehensive than anything that has been previously used in models. And so hopefully we can move past maybe only modeling the inferior conjunction and superior conjunction, and maybe focus on a little bit more detailed phase resolved analysis. The last gamma ray binary I want to talk to you about is one that I wrote a paper on, which is high mass gamma ray binary J1405. It is one that Robin actually discovered. It has an O-type companion with a roughly 14-day orbital period. Its intrinsic brightness is close to that of LS5039, but it's quite far away. Here's the spectral classification, comparing it to another 06.5 type star. And so that was kind of the basis for our classification as such. It was found in a blind periodicity search. Oops. And on the top, we see the Fourier power of our orbital period, reaching almost a 99.9% confidence interval. The orbital phase-folded light curve is shown here on the bottom left. The GeV, gamma ray emission, MEV, and GeV light curve down here shows two kind of peaks. One, much weaker than the other. And then there's the Swift light curve that kind of shows that the MEV and GeV and X-ray light curves are anti-correlated. So we ended up doing a phase-resolved fit, so kind of like what we saw for LS5039, and we found that there was very little spectral variation outside of the normalization, outside of the flux, and that second gamma ray peaks significance is diminished. We also had some X-ray observations that allowed us to make some assumptions based off of for the geometry, so we could better model the broadband SED. We didn't find any evidence of a spectral break, so up until 20 keV, so we were able to put a limit on the magnetic field, suggesting that the magnetic field at the intrabinary shock is at most 2.7 Gauss. We assume a fairly simple circular orbit and a 1.4 solar mass compact object with an orbital separation of about half an AU. And then we model the X-ray, gamma ray data with synchrotron and inverse Compton models, radiative models with two particle populations, the pulsar wind and the stellar wind. And we actually end up doing a fairly good job fitting the X-ray data and the gamma ray data. There's also some HESS data that hasn't been published yet, but it seems to be fairly well aligned with our kind of TeV drop off here, our what we see in our best fit results. And so that's a little over my time, but to end, I just want to kind of leave us with some research ideas that some people I know in the field are looking into. Obviously, HMXB is a brand new kind of toy that we get to play with, looking at the polarization of the geometry and intrabinary shock. There's some new star observations of HESS J0632. Just getting more exposure time gives us TeV, GeV, MEV kind of information, and there are a couple more HMGBs to study, LMCP3, J1018, who, if you have any questions, you can ask Joel about. And there's always going to be better breakthroughs in modeling and that sort of thing. And so I'm just going to leave it here to thank my collaborators, and I'll take any questions.
Thanks very much, Alex. Very nice presentation. And for people in the audience, I should point out that Alex was rather modest in his presentation, and also the work on 1405 appeared in the paper that Alex led, appeared in the Astrophysical Journal not so long ago, and some of the new star data which is upcoming was obtained by a proposal that Alex was the lead on there. So Maybe a little bit of an understatement there, if you want to see Alex. So I invite questions on Alex's paper primarily, but also if you've thought of some questions for Joel's paper as well, please go ahead, maybe raise your hand.
Stop sharing.
Or you not seeing anybody at the moment. So I have a question then in the meantime.
Mhm.
Um, For HESS J0632, I think your diagram showed, was it showing the disk is aligned with the orbit? So it would be unlike PSR B1259.
Um, yeah, I think that was from Adams at all 2021. This kind of geometry that I showed. Was that what you're referring to, I think?
Think it's just, yeah, this one there, yeah.
Yeah.
It was like for PSR B1259, there's this offset is shown in the animation you showed. I couldn't remember what the geometry is thought to be or what sort of handle we do have on it.
Yeah, I'm not entirely too sure why it looks like the disk is kind of in the plane. Um,
I mean, it's a 2D plot, but maybe that's a
yeah,
limitation there.
right, exactly. So I'm not entirely sure, unfortunately.
Okay, thanks.
Yeah, I did end up using a couple of the animations for sources that this is also B1259 though.
That's a nice animation.
Yes, it is. I think I didn't credit it here, but I did in an earlier slide because I used it
Okay.
twice. Yeah, no, that's a good question. I don't have an answer, unfortunately.